let's apply this definition of chi-squared to the table we've been working on. So here's our observed, here's our expected. Here for each cell is observed minus expected divided by the square root of expected. I haven't squared it yet because sometimes it's nice to see which ones are positive and which ones are negative to tell you which cells are higher or lower than expected, assuming independence. And then we could make another table where we square each of those and then sum them all up. But Excel has this handy function called sumSQ that will square each component and then add it all up. So we get a chi-squared value of 1.38 here. And then the question is, that's a measure of how far this table is from this table. Is that a long distance? Is 1.38 large? Is it so large that we'd say, oh, this table definitely wouldn't have come from sampling from a population that truly has independence? So is 1.38 large? It's kind of hard to say. Another thing to look at is the sample size. So here I've hidden some calculations that what if all these numbers were 10 times as big. So if our data set was just 10 times bigger, but with all the same relative frequencies, then here's our expected values. They're 10 times bigger than that. And then our final chi-squared is 10 times bigger than that. So is that too large to say that this table could plausibly have come from that table? So we need to know, how does the chi-squared value tend to behave to know what's typically large and not large? And that's our next tab. So we're saying chi-squared is a standard normal value squared plus another standard normal value squared, maybe two of those terms, maybe only 3 or 4. So let's go look at this chi-squared distribution. I have a calculator for it here. If we are only adding one squared normal, it turns out that has a distribution that looks like this. It's highly skewed. If we're adding 2 of them, it's still skewed but not as skewed. If we're adding 3 of them, then it's kind of more bell curved. If we're adding 4 of them, it looks like that. If you've taken a calculus class with me, we've called these surge curves. It's basically the same thing. And as we add more and more things, the average gets bigger. Like here we are adding 15 of them, and it turns out the mean is about 15. And it's getting more and more bell curve shape. But usually we're down in this region where we only have 3 or 4 of them or something that we're adding together. So that's how chi-squareds behave. This parameter is called the degrees of freedom, which sounds like something we were doing with the t-distribution back in chapters 9, 10, and 11. And it's related, but not in a way that we really want to handle here in Math360, stat360. So what degrees of freedom do we want to use? Well, if our table is 2 by 2, and we want to have the same numbers here in the lower margin and the side margin, if I just tell you this number, then you can figure out what this number is, so it totals up to this, and you can figure out what this number has to be, so it totals up to that. And then, since you know 3 of those, you know the 4th. So really, just telling you one number tells you about every other number in the table to keep the same marginal values. So you really only have 1 degree of freedom there. And we saw that the chi-squared distribution looked like this. If you have a 2 by 3 table, you could set this number and that number, and then figure out all the rest of them so you can maintain the same row and column totals. It feels almost like doing Sudoku at that point. So there you only have 2 degrees of freedom, and the distribution looked like this. If you have a 2 by 4 table, you have 3 degrees of freedom. If you have a 3 by 3 table, you can manipulate those, and then the rest of them are set. So, and here's what it looked like in the distribution. So looking at these examples, what can we say is the degrees of freedom for a table that has R rows and C columns? Is it just R times C? Well, you actually lose a row and you lose a column, so the degrees of freedom is actually rows minus 1 times columns minus 1. And the mean of the distribution is just the degrees of freedom. So the larger your table, the larger you would expect chi-squared to be, even if you're just random sampling. Now chi-squared is a continuous distribution, but the numbers we're doing are integers in the observed table. so they're kind of chunky. To be a good approximation, we need the numbers to be large enough, and the usual guideline is that you need the expected value in each cell 5 or more for the chi-square test to be valid. So once you've computed your chi-squared value, how do you compute a p-value? Well, Excel has a function called chi-dist, where you give it your chi-squared value and your degrees of freedom, and it tells you the value from that chi-squared value up to the right, unlike norm dist and binom dist, which are always to the left, so that's confusing. And that is the p-value. So here, our chi-squared value was this, and we had 3 rows and 2 columns, so 2 degrees of freedom. And so our p-value is 0.499. So think about how you would phrase your hypothesis test conclusion there. Maybe write it down for yourself. I'm going to pause the video. So you'd say, since the p-value of 0.499 is larger than alpha of 0.05, we fail to reject the null hypothesis. We do not have sufficient evidence that the table shows association. If the sample is 10 times bigger, we still have the same degrees of freedom because the table is still the same dimensions, but now our chi-square, we're much farther out in the chi-square distribution, so our p-value is smaller. So how would you phrase that hypothesis test conclusion? Go ahead and pause the video and think of it. Welcome back from pause. You would say, since the p-value of 0.00098 is less than alpha of 0.005, we reject the null hypothesis and say that we have sufficient evidence to say that there is association in the table. In the next video, we'll show a shortcut about all that.